But one of my connection with him is he was the handling editor of my first accepted paper. So because of that paper, I could survive in this academic area, and that's the reason probably the reason I can be here now. So thank Fred again. So today I'm going to speak something about the cohomological homotopy rigidity problem for toric varieties. And I see many experts in toric topology in this room, but on the other hand, I think that there are many people who are not the area of this toric topology. So I prepared really elementary talk for the first half of my talk. Thank you. So please sit back, relax, and save your energy for the next remaining 2 talks after the coffee break. Okay. So just elementary sentence in algebraic topology. There are many topological spaces that are indistinguishable by the cohomology rings, of course, just too much obvious. For instance, if you think about the lens space and 3-sphere, the rational cohomology do not distinguish between these two, right? So some people may ask, like, okay, lens space have some torsion in the middle degree, and you are taking the rational coefficient, so this ignoring all the torsions. So what if you take the rational integral cohomology ring instead of the rational cohomology? But even if you think about the integral cohomology, you can think of the 3-sphere and homology, Poincare homology sphere. So that does not distinguish between these two. But you may ask, okay, 3-sphere and Poincare homology sphere, they don't have any cup product structure because it only have 0 degree and top degree. So what if you think about the manifold or variety, whatever, having some non-trivial ring structure in the middle, right? What I can think of is weighted projective space. For instance, if you think about the weighted projective space with weight 1, 2, 3, and 1, 1, 6, they have isomorphic cohomology ring over integers, but they are not homeomorphic. So all I want to say for this part is wherever you're working on, I don't think it is difficult to find such an example. Okay, but surprisingly, if you think about the toric variety, smooth toric variety, if you restrict your attention to the class of smooth toric variety or quasi-toric manifolds, then surprisingly there are no examples like that. So all the toric variety, smooth toric variety, having isomorphic cohomology ring, we don't know whether they are really homeomorphic or not. There is no counterexamples, right? So this is the question, so-called cohomological rigidity problem, right? So this is completely opposite from our common algebraic topology common sense, but still we don't have any counterexamples. So for the first half of my talk, let me first try to convince you in what sense this problem makes sense in toric topology. And then after that, I will try to introduce some of my contribution with my collaborators. Okay? So what is the toric variety? Just a definition. So this is an algebraic variety, complex algebraic variety, and containing algebraic torus as an open dense subset. And in this open dense subset, there is a natural algebraic torus action, and then it has to be extended to the entire variety. So if some variety having this satisfying this condition, that's going to be your toric variety. But I know that this definition is too abstract, so it's rather difficult to feel the real flavor of this toric variety. So I just summarized this definition into simple diagram. First, you think about the coordinate multiplication on this algebraic torus, right? And then if this coordinate multiplication can be extended to the action of the entire variety, that's going to be toric variety. Okay, just a simple definition. And in topology, we usually think of the compact torus section instead of the algebraic torus section because we can play with some OB space. And also there are many reasons for this. But anyway, let's try to think about the compact torus section. For instance, when n is equal to 1, right, the easiest example, just C star, that's going to be toric variety, right? And also, you can add the origin to this complex, this C star. That's going to be, that's another toric variety having one fixed point. And also, you can add one more infinity point. That's going to be another toric, one-dimensional toric variety having two fixed points. That's all about the one-dimensional toric variety, right? And also, we are considering the compact torus in this case just a sub-collection. That's going to be just a rotation, right? So this is one-dimensional case. When X is projective toric variety, then as you may expect, you can think of the quotient space, but there is a nice equivalent relation between the orbit space and convex polytope. So here I just emphasize the equivalent. It's not a mathematical statement at all. There are so many correspondence between these two. I would say, roughly speaking, that's all about toric topology and toric geometry to understand what this equivalent is. So for instance, when n is equal to 1, we can think of the rotation of the sphere, and the orbit space gives you the interval, one-dimensional polytope. And this one-dimensional polytope is not just a combinatorial object, but also it has some phase structure. So for instance, if you think about the two end vertex that represent a fixed point, and then if you think about the point in the interior of this edge, that's going to be just a free orbit. So that kind of information, that's something we can understand from the orbit space. But this is too simple example. But if you think about the two-dimensional case, then orbit space, now the dimension of the orbit space is dimension 2. So for instance, for the case of weighted projective space, you can think of the two-dimensional torus section, and the orbit space is going to be just a triangle. But remember that I'm not just looking at this triangle as just a combinatorial object, but I'm looking at this object as an object sitting inside certain vector space together with a lattice structure. Okay? So I'm looking at like this. So my object, my convex polytope is exactly the object sitting inside the vector space together with the lattice structure, which means that this polytope has a geometry. My geometry means the location of vertex and the direction of co-dimension 1 faces. That's all about the toric variety. Okay. So this is one direction, like how to obtain a convex polytope from the toric variety. But there's opposite direction as well because it is equivalent. So one way of constructing toric variety from the convex polytope, we can follow this construction. So when X is projective toric variety, and then we can think of the image of the algebraic moment map, right? And then topological construction of the toric variety is first you think of the product, just Cartesian product of polytope together with the dimension P, the torus having the same dimension as the dimension as my polytope, and then take some quotient relation. Okay, and this equivalent relation looks a little complicated, but we have some nice picture. So, for instance, if you think about the pentagon, right? Remember that my pentagon is not just a pentagon, but also this is a geometric object having all the different directions. Normal vector for co-dimension 1 faces. Okay, so my lambda 1 is the normal vector for the hyperplane supporting these co-dimension 1 faces, and then lambda 2, lambda 3, lambda 4, and lambda 4 have that information. And then if I have this ingredient, the way how I construct a toric variety is to take a Cartesian product with a two-dimensional torus, okay, and then I'm going to collapse certain subtorus by this equivalent relation. So what this equivalent says is, if I have this lambda 1, remember that I'm looking at this object as an object sitting inside the Lie algebra. So each direction determines the circle subgroup generated by this lambda 1 direction. So I'm going to collapse the circle subgroup generated by this lambda 1 here, right? And then so this two-dimensional torus gives me certain one-dimensional object, and then for instance, the two-dimensional torus corresponding to this vortex have two independent direction collapses at the same time. That's gonna be a point, right? So this is the way how I understand four-dimensional object in a two-dimensional picture. Okay, so probably you remember this picture from yesterday's Shin's talk, but you know we are collaborators. Oh, probably I forgot to say my collaborators. Like this talk is based on the joint work with Shin Fu and Larry So and Stephen Terrier. So so do you have any questions so far for this construction? So I want to emphasize that this kind of construction is something you can do no matter whether the variety is smooth or singular. Okay, so all right, so remember that we have to be able to understand some topology and geometry out of the combinatorial or geometric information of the polytope. So for instance, the smoothness is exactly whether the polytope is Deljunct or not. So what is the Deljunct polytope? So first one is a Deljunct. Second one is not Deljunct, because the Deljunct, in order for a polytope to be a Deljunct polytope, it has to satisfy two conditions. One is at each vertex, okay, at each vertex, there has to be exactly dimension many outgoing edges. Okay, so here I have two-dimensional object, and for this vertex, I have two outgoing edges, two outgoing edges, and two outgoing edges. This is one condition. And the second condition is if you think about the primitive vector, outgoing primitive vectors for the edges at each vertex, that has to form an integral basis. Okay, so this 1, 0, 0, 1 is basis, negative 1, 0, negative 1, and 1, negative 1, this is basis, and then this also basis, so this is a Deljunct. However, if you look at the second one, that's not going to be Deljunct, because if you look at the top vertex, you know, 0, negative 1, 2, negative 1, it's not a basis. So it doesn't satisfy the Deljunct condition. The third picture is not simple, because the simple polytope means whenever you have a vertex, then there has to have the dimension many outgoing edges. But if you look at this top vertex, we have 4 edges, but the object is a 3-dimensional object. It's not simple polytope. Okay, so this is a combinatorial hierarchy of the in the level of polytope. But what you can see from this information is Deljunct polytope gives you a smooth toric variety. Okay, and then if the polytope is simple but not Deljunct, the corresponding variety is a singular variety, but at worst orbifold singularities. Okay. If you have some polytope which is not simple, that's something very, very singular variety beyond orbifold singularity. Okay. And also, let me try to explain a little more topology about the smooth toric variety. So for the case of smooth toric variety, so there's a nice formula for calculating the equivariant cohomology ring. Because we have a variety having torus section, we have to be able to compute the equivariant cohomology corresponding to this torus section. In this case, the toric variety, the equivariant cohomology for the toric variety, smooth toric variety, is isomorphic to so-called Stanley-Reisner ring. So Stanley-Reisner ring is just nothing but the truncated polynomial ring, and then variables are corresponding to the codimension 1 faces. This FP is my notation for the set of codimension 1 faces. And the ideal is generated by square-free monomials. And then this monomial is nothing but whenever you have a bunch of facets which do not have common intersection, then that's going to be the generator for this idea.
So on the previous slide, you probably defined X of D, right? And if you want X of D is something, it's a toric variety such that when you take the quotient, you get P again, right?
Yeah.
But maybe there's other toric varieties that also have that property. I mean, how unique is this? Like, the X sub D is just one way of defining that, right?
Yeah, for the let me just okay, probably if I understand correctly, all toric variety can be obtained in this way or not, right? So yes, if in this talk, let me just stick to the projective toric variety case. The projective toric variety case can always be obtained in this way, just the underlying topological space. So if you get out just if you think about other class of toric variety like the non-compact toric variety, it's not corresponding to the yeah.
So then a follow-up question is, if D is not del size, then you're saying there is no smooth toric variety at all,
right?
Whose quotient is D.
Right. There's always O before.
Could you please repeat the question?
Oh, sorry. Okay. He was asking about. Oh, sorry. Going backward. Okay. He was asking about this correspondence, right? This correspondence. If we have a simple polytope which is not Daejang, right? That's equivalent to say that the corresponding toric variety is an O-bifold. It's equivalent. Okay. All right. So, okay, where are we now? So we can think of the equivariant cohomology corresponding to this torus section, because the toric variety have a natural torus section just by the coordinate multiplication on the first vector in the Cartesian product. So we have this, we can think of the equivariant cohomology. In this case, it's isomorphic to the standard-Reijner ring of the simple polytope. Okay, the standard-Reijner ring is this definition I told you before. Sorry. For instance, the standard-Reijner ring for the square is just because we have so many facets, right? And then so we have to prepare 4 variables in degree 2, x1 through x4. And then if you just index the facet in a counterclockwise or clockwise, then x1 and x3 do not intersect each other. That's going to be my generator for this idea. And then x2 and x4, that's another idea, right? So this is not, for instance, if you try to explain the polytope to the middle school student or high school student, then how do you explain it, right? So you first prepare a bunch of hyperplanes, and then you may be able to explain, okay, this collection of facets intersect, and then they intersect, and they intersect, right? On the other hand, another way of explaining is, okay, you prepare a bunch of facets, and then some subset of facets do not intersect each other. Then some, right? So this is another way of describing a polytope, opposite way. So this is exactly the algebraic model for the second description. Okay. So let's go back. Let's go to the singular ordinary singular cohomology. So if you have whenever you have a TCW complex and then vanishing odd degree cohomology, then because of this condition, vanishing odd degree cohomology, you can think of some spectral sequence and they degenerate in E2 page. So singular cohomology can be obtained by the equivariant cohomology by killing the H star BT algebra structure, right? So in this case, remember that my equivariant cohomology is isomorphic to the standard-Reijner ring. And also this H star BT, as many of you already know, this H star BT, the classifying space of the torus, its cohomology is just a polynomial ring with dimension many variables, right? So in order to understand this H star BT algebra structure, I have to be able to understand what this pi star in terms of this at the level of this one, right? So if you analyze this algebra structure, then if I take some generator in this polynomial ring, and then it goes to some linear combination of degree 2 generators. But here, if you look at this one, there's some information about the geometry. So remember that equivariant cohomology is isomorphic to the standard-Reijner ring. That's all about the combinatorics of the polytope. There's no geometry, just the combinatorics. But if you look at the singular cohomology, not just a singular cohomology, it's algebra structure, H is a BT algebra structure. That's the place where you can see the geometry of the underlying polytope, right? In this idea, right? So for the case of smooth toric variety, my singular ordinary cohomology is isomorphic to the equivariant cohomology modulo this algebra structure. That's going to be just a polynomial ring modulo two types of ideals. One is the ideal comes from the combinatorics of the P, and the second ideal J that have some information about the geometry. So remember that topologically or geometrically as well, the toric variety is all about the polytope, right? But here in this cohomology, it contains both information in such a way that we are forgetting this information by quotienting the idea, right? Somewhat opposite direction. So again, toric variety is all about the polytope, but this cohomology has some information about this combinatorics and geometric information of this polytope. So we have this cohomology must determine the topological type of the toric variety somehow. So that's just a basic philosophy. Yeah, just an easy exercise. Like this is the picture for the Hilbert surface, 4-dimensional space. In this case, I have 1 and 1 and 0, 0,1 and -1, 0 and 0, -1 and this Hilbert surface. And then the cohomology is very simple. Like we have one type of ideal and the second type of this ideal. And then this ideal I determines the combinatorially, okay, the polytope has to be the square, right? And then this ideal, second ideal has information about the 1,1, 0,1, and then -1, 0, and the 0, -1, right? So this is the way how we see the geometry of the polytope from the cohomology. All right, so you have any questions so far? Okay. So okay, let's look at the cohomological rigidity problem again. So if you have a smooth toric variety X and Y, and then if they have isomorphic cohomology being, then whether we are asking whether they are homeomorphic or diffeomorphic, we still have no counterexample. On the other hand, there are many papers supporting this conjecture, this question. So for instance, recently we have a paper for the strong cohomological rigidity for Butt manifold. Butt manifold is a toric manifold corresponding to the product of the n cube product of one simplest. And the second one is just a probably three-dimensional Pogorelov polytope. All the toric manifold corresponding to three-dimensional Pogorelov polytopes, they are cohomologically rigid. Right? And also a two-stage generalized Butt manifold, they are cohomologically rigid. So yeah, I'm just picking up just randomly 3 papers, but there are many results supporting this conjecture. But on the other hand, there is no counterexamples. Okay. All right. So this is just a classical story. What's going on in the original version of the cohomological rigidity conjecture? But at some point, I was thinking like, why it has to be a smooth toric variety, and also why we are asking homeomorphism or diffeomorphism, right? Remember that singular cohomology is kind of homotopy invariance, so it is much natural for us to ask homotopy equivalence before we ask the homeomorphism or diffeomorphism, right? So let me try to modify the original question. We call it like cohomological homotopy rigidity problem. So drop the condition of the smooth toric variety, and then let's make this triangle diagram. Before we go to the homeomorphism or diffeomorphism, we just pass through whether we can pass through this homotopy equivalence or not, right? I would say this is much more natural question. But if you remember my previous slide, then all the nice story begins with the identification of the equivariant cohomology with Stanley-Reisner ring. But for the case of singular toric variety, integer coefficient equivariant cohomology ring is not isomorphic to the Stanley-Reisner ring. And also it is not generated by degree 2 element. Even it may have non-trivial odd degree cohomology, so that it's rather difficult to apply the spectral sequence just directly. Furthermore, if you broaden your category to the singular toric variety, there's a counterexample, right? So I already gave you the hint for this counterexample in my very first slide. That was the weighted projective space. So weighted projective space is a singular toric variety having orbifold singularities. But for instance, weighted projective space 1, 2, 3, 1, 1, 6, they have isomorphic cohomology rings, but they are not homeomorphic. But according to the nice classification results from Barry and Franch, Nottebohm and Ray, these two spaces, CP 113 and 116, they are homotopy equivalent. Not only this space, but also all the weighted projective spaces, their homotopy type is determined by the cohomology ring structure, right? So we have a chance for the singular variety still, for the question of homotopy equivalence, right? So, I want to introduce some of my contribution to this direction. So one is, okay, let's try to think about the easiest, lowest dimension we can think of. One dimension is there's nothing other than just sphere for the case of projective space. For the case of projective toric variety, one dimensional is just a sphere. So next stage is a two-dimensional, complex two-dimensional. So what we could prove is for the case of four-dimensional toric variety, real four-dimension, I mean, if it doesn't have any two torsion in the H3, then we could prove that the cohomology ring isomorphism implies the homotopy equivalence between these two varieties. Let me briefly explain how we get this statement. Just one simple example, right? So if I have this four-dimensional object, four-dimensional toric variety, this is a manifold example, but it's okay to work with the orbifold, whatever. So if you think about this two-dimensional the two-dimensional polytope, and then what the picture that I showed you before is something like this. In the interior, there is a two torus. There's no equivalent relation in the interior. But the boundary, there is an equivalent relation. I'm going to collapse one circle subgroup generated by, for instance, this 1, 0, right? Then I'm going to collapse the second coordinate circle in this case. So I have one-dimensional torus here, and then similarly like this, right? But this picture gives us some nice homotopical interpretation of this space, right? So if I decompose this space into two pieces, one is if I pick up one vertex and then I'm just taking, I just subdivide it into two pieces. One is the union of all the faces containing this vertex and the rest of them, right? And then this is locally look like R2 positive, and then the rest of that is just a union of two edges. And then if you look at these two edges, that's going to be just a wedge of two spheres, right? And also, if you look at if you just imagine some line connecting some point here and some point here, then that's going to be, just think about this, the line, and in the interior there is a two torus, and then one end is a collapsing the first coordinate circle, and then the other side is collapsing second coordinate circle. That's going to be just the definition of the join. So we have three spheres, right? So entire space can be understood as just a mapping cone of certain attaching map from S3 to wedge of two spheres. So this is homotopical interpretation of the four-dimensional toric variety, right? So we have this co-fibration, right? And then at the level of cohomology, we can think of natural basis, cohomology basis coming from the cellular structure, right? So let's say U1, UN, they are cellular basis for H2, right? Coming from this S2. And then V to be the basis in H4 coming from this S3, right? And then since we are talking about the four-dimensional cases, it is rather natural to think about some sort of intersection form, like bilinear form for the coproduct structure. So we call this, let's call this Q of X. The bilinear form corresponding to this H2 tensor H2 goes to H4, right? So this is just a bilinear form. If you fix a basis, that's going to be represented by a square matrix, symmetric matrix, right? We call this bracket QX. It's just a square matrix, symmetric matrix. So we have this information. But if you look at this co-fibration, right? This co-fiber, the toric variety up to homotopy type, right? So this is nothing but the mapping cone of this one. So that if you want to understand the homotopy type of this toric variety, that's all about pi3 of S2 wedge S2, right? Because this is a mapping cone of S3. So we can naturally think of the Hilton-Miller theorem to compute the pi3 of this guy. So this attaching map is homotopic to the linear combination of a bunch of maps, like some Hopf component and Whitehead component, right? And then there should be some coefficient for this linear combination. And then what we could verify is we have this symmetric matrix, right, for the product structure. On the other hand, we have this result for the Hilton-Miller theorem and then we have this coefficient, and then they agree, right? So this coefficient goes to the diagonal element, and then off-diagonal element corresponding to this Whitehead component. So roughly speaking, if you have two toric varieties X and Y, and then those two are mapping cones for certain attaching maps, and if you assume the cohomology ring isomorphism, then that's gonna be two intersection matrices has to be conjugate, and then that will imply the homotopy equivalence between these two spaces. So that's brief sketch of the proof we made, right? Okay, this is the lowest dimension which we can think of, and then let's not make any restriction on the dimension. What is the simplest case, right? So probably the simplex, but that corresponds to the weighted projective space. So that's done by the result of Barry and Frantz and Nottebohm and Ray, the classification for the weighted projective space. So probably the next case is going to be the product of simplices, right? So this is our second approach. So if you think about the toric manifold, M and N, corresponding to the product of same dimensional simplices, okay? And then if you think about, but in this case, if you think about the product of d-dimensional simplices, and then I take L times product, that's gonna be the complex dimension of these smooth toric varieties are d times L. Right? The real dimension of the orbit space is d times L as well. But in this case, let me just prepare some set of prime numbers, which is less than the set of primes, which is less than or equal to n minus d plus 1. Looks at the moment looks a little artificial, but what we could prove is if you assume the cohomology ring isomorphism between these two, then we could prove that they are homotopy equivalent after certain localization. Okay. We couldn't reach out to the just the honest homotopy equivalence, but we could prove that after certain localization, there is a homotopy equivalence. So for instance, if I take the delta 2 times delta 2 times delta 2, we have the, in this case, I'm just do some exercise for collecting the correct prime numbers. In this case, just 2, 3, 5. So whatever the toric manifold is, all the toric manifold corresponding to this delta 2 times delta 2 times delta 2, they have the rigidity property, but after certain localization. And then the way how many prime numbers which we have to invert, that in this case, this is nothing but 2, 3, and 5. Okay. So just one page summary for the proof, like assuming the cohomology rings are isomorphic, then we have to construct a certain homotopy equivalence between these two after certain localization. We use some skeletal co-fibration and then mathematical inductions. Remember that every smooth toric variety is concentrated, cohomology is concentrated in even degree, and then they are simply connected spaces. So we can think of certain CW complex structures consisting only of two-dimensional cells, right? So we can skeletal inclusions, even dimensional skeletons, right? So so the first row is for the co-fibration for the first manifold, and the second row is the co-fibration for the second manifold, and then we want to connect these two, right? And then if we have, because this is a co-fibration sequence, co-fibration diagram, so if you have a map between the first horizontal map and the second horizontal map, that's going to induce a map in the last horizontal map, vertical map, I'm sorry. Okay, so the first map is something you can construct from the cohomology ring isomorphism. And then assuming that there exists a map in the middle, then you can construct the third vertical map, and then do the same construction using the mathematical inductions. And remember that we need to invert certain prime numbers. Okay, so in the process of doing mathematical inductions, when we pass through the degree from D to 2D to the 2D plus 2, from B to C, from this to this, right? And then we have some obstruction. What was the specialty for this D? D was the dimension of the simplices, right? And then there should be some obstruction to continue this induction process. So that's the place where we need some localization process, and then use the 5 lemma and the Whitehead's theorem to show that the last map, the C map, the last map is homotopy equivalence. So this is the way how we get the proof. Okay. So instead of getting more details about this proof, let me just briefly explain more bigger picture for this project. Okay. So if you are familiar with some rational homotopy theory, then every toric manifold is rationally formal, by the result of Taras and Buxtehude, Ray. So what this rational formality implies is if the rational homotopy type is exactly determined by the rational cohomology ring isomorphism, right? So if you have the graded ring isomorphism, then we can think of the quasi-isomorphism between these two with the zero differential in CD, in the category of commutative differential graded algebras. And then you can think of the APL model, and you can think of the minimal model, and then they has to be, because these two are isomorphic, then so this minimal model has to be isomorphic in the CDGA. So their rational homotopy type is determined by the rational cohomology ring, right? So rationally, for the case of smooth toric varieties, there is nothing to do for this rigidity conjecture. But we want to do, if we do not want to do some rational, if we don't want rational homotopy classification, but if we want to do some classification over honest homotopy equivalence, right? That's what we want to do. So we may be able to refine the question. So this bottom line is the rational homotopy theory. So this is true, right? For the case of toric manifold, we have this one. We want to lift this arrow to the integers, right? We don't know whether this is true or not. This is the question. So before asking the homotopy equivalence between these two out of the ring isomorphism between these two varieties, maybe we may be able to ask okay, there should be some prime numbers which we have to take localize so that this diagram commute, right? So that's probably some project which is doable, right? So the precise question is find some obstructions or prime numbers to make this upper arrow commute. Like it's not quite precise, but to make this arrow to be true, to be more precise. Okay. So yeah, so let me just summarize all the results which we have so far. So the way how I approach this cohomological rigidity problem is just I am somewhere in this map, right? So we start from the origin, and then either we can think of the complexity of the underlying combinatorics, or we can increase the dimension, right? So at the bottom dimension, in the dimension 2, right? So we have some partial results for the 4-dimensional toric variety case. And then we have another result for the 6-dimensional smooth toric varieties over the Pogorelov-Politov, right? But we do not know anything about the higher dimensional. But if we minimize the complexity of the toric variety and then think about the just to increase the dimension, that's going to be the projective space, weighted projective space, or some manifold over product of simplices, right? That's probably the next step. And then there are some partial results on this shaded area, but you know, the question itself is very, very widely open, right? So, all right, still have some 5 minutes, but it's better to have more coffee break. Let me finish here. Thank you.